Alright, so we're going to be introducing a completely new topic within the realm of calculus, right? We spent so much time learning about limits and what they can do, right? They can do derivatives. They're helpful in integrals. Now we're going to see the third power of limits, which is sequences and series. But today we're only going to be talking about sequences and get a solid understanding about this. So we're only going to be looking at the first half. Sequences. So a sequence, let me write this down as a definition. This is a definition. A sequence, and we also write it as this. So this is how we write a sequence with the curly braces. That's kind of weird. We don't really use that too much. So it is the list of numbers in an explicit order, right? So the way we would write it is the sequence A, oops, that's a bad brace, is basically the first term, the second term, the third term, and we keep going until the nth term, right? But actually we will kind of want to keep going. This is how we write it, right? This is the first term, and then second term, third term. This is the nth term, right? If I ever want to talk about the nth term, it's kind of like a placeholder, right? We want to talk about the nth term. In calculus, we're not really focusing on only n terms. We're kind of seeing what happens when that goes into infinity. What kind of sequence does these numbers go to when you go to infinity, when the nth term is actually infinity? We call those infinite sequences. So this is also important to know. Infinite sequences. So its definition is basically sequences with domains, right? The inputs. Let me scroll this down now. There we go. With domains that are infinite. But specifically infinite subsets of positive integers, right? And what I mean by infinite subsets of positive integers is that you don't want your nth term to be 1/2, right? There's no such thing as a 1/2 term. We care about 1, 2, 3, 4, 5, right? Those are integers that are positive, right? That's what we care about. We care about those types of terms, not like 0.5, that term. We don't care about the pith term or the eth term, I guess is what you would call it. We only care about the integers. So that's what I mean by subsets of positive integers, right? And we keep this going, so we go out to the thousands, we can go to the millions, the billions, the trillions, and so on, right? So that's the idea of an infinite sequence. But we're going to be looking at some finite sequences first. So with our first example, we kind of want to look at a simple sequence. Let's say this is, the sequence is defined as this, right? -1 to the nth power over n squared plus 1, right? This is our first example we'll be looking at. And what I will be asking for is, what are the first three terms, and what is the 100th term? The 100th term. Right, so I'll write the solution in purple. So we can this is not too bad, right? Just set what's a of 1, right? And that's just kind of like what is the function of f, or f of 1 kind of the thing. That's kind of like the style, but this is the notation we want to keep consistent. right? So this is -1 over 2, right? That one was pretty easy. We can just keep going. -1, 2, 2 squared plus 1. This is now positive. This is positive. This, right? 1/5. And then the third term. And then this is what? 3 squared plus 1, that's 9, so it's 1/10, right? And then we have to keep the negative because this is now a negative term. Notice that this sequence is flip-flopping from positive, negative, and positive, negative. And this is because of this term right here, right? A lot of problems deal with something like this. They have like this flip-floppy term right here. And this is one example of it. And we'll see this a lot when we're looking at series and sequences, but mostly series. And then of course we want to find the hundredth term, right? So that's just -1 to the 100th power. It's even, so we know it's basically positive. And then this is a positive 1 over, right? This is, what is this, 4 zeros, like this? Yeah, that is it. So that's our first example. Alright, so the next thing we're going to be talking about, let me just see if I can do this well. Is we're going to be looking at two things. Wait, let me just try that again. Alright. Come on, computer. There we go. So, oop. Alright, so the next topic we'll be looking at that deals with sequences are something called explicit and recursive. So I'll give you an example. It's probably best to know if you see an example. Well, the explicit one is when it's just defined in terms of n. So the sequence defined by n. We saw that in the last example. That was an example of explicit sequence, meaning that just n is kind of like the function f of x, right? You just plug in a value of n, and then you can get your answer. On the other hand, recursive depends. It's a sequence. Let me write this: sequence that depends on past terms. Right? So by past terms, it's kind of like a good example, right? So this is an example of a recursive one, right? So I'll say name the first 4 terms of the recursive sequence defined by so this is what it's defined by. It's defined by the first term, B1, right? You can use any letter. I'm using B in this case. So the first term is 4, B, the first term, and then the nth term is defined as the previous term added by 2, and then I have to add this condition for all n greater than 2. And the reason why I add that condition at the end is because you can't have a 0th term if I put in 2. I mean, if I put in 1, right? If I put in 1, then this term is there's no such thing as a 0th term in this case. So let me scroll this down and we can try tackling this problem. Okay, so I'm going to still do it in purple, right? So we know the first term, they gave it to us. B1 equals 4. So what is B2? B2 is precisely equal to B2 minus 1 plus 2, right? Which is equal to B 1 plus 2, and we know what b1 is right here, right? We can just plug that in to get our second term, which is 6, right? And then we do that same process. b3 is equal to b sub 3 minus 1 plus 2, and we found out was 6 plus 2, which is equal to 8, right? And then the final term, the fourth term, equals b4 minus 1 plus 2 equals 8 plus 2, right? And so forth, right? If I ever ask you to keep going, you know how to keep going. Why did it go up? Let me just go back down. There we go. And that's probably all I'll do for this video. And in the next video, I'll start increasing our knowledge on sequences and getting used to more the basics before we get into calculus of sequences.